This is Crystal Chern,
And this is James Shu.
and here is our final project for CS289A, Introduction to Machine Learning for spring of 2022.
Our project name is Machine Learning Classification Techniques for Damage Assessment in Structural Health Monitoring.
The motivation for this project is to improve the process of structural health monitoring in the event of a natural hazard. When a hazard occurs, we'd like rapid damage detection. Machine learning techniques can allow us to quickly predict damage based on vibrations of a structure. In the past few decades, more and more structures have been instrumented with vibration sensors that allow us to perform structural health monitoring with automated data science methods like machine learning.
To achieve this damage classification task, we've established this following framework. Provided an example situation of a bridge with structural properties and a set of example events of earthquake ground motions, we apply these examples to a test bed of either a structural analysis model or the physical structure itself. After this application, we obtain a dataset of features and labels. The features are acceleration response histories that show the level of shaking response, and the labels are damage states that show the level of damage in the structure. Now we can train machine learning models to perform this damage classification task. In the end, when a new situation occurs, the hope is that the machine learning model can accurately predict damage states rapidly.
The dataset that we used for this study includes 755 data points with 45 extracted features called demand measures. These features correspond to the intensity of structural vibration. The data labels come from simulated strain responses at the bridge, and based on material properties of the concrete and steel, we can assign damage state labels.
The first machine learning technique that we applied was decision trees, which help substantiate the use of at least two features that likely have a strong relationship to the physics of the structure itself. These include peak response velocity, standardized CAV, and cube absolute acceleration intensity.
We also applied lasso regression and found that peak response acceleration, Arias intensity, and instantaneous power have good predictive power for damage state labeling. We also see that the peak response velocity and standardized CAV coefficients are non-zero, which is consistent to what we found in decision trees.
One other thing that we looked at was class separability through PCA. We found that there is a fair amount of class separability, especially between damage states 0 and the rest.
One final technique that we applied was hyperparameter tuning for Lasso's regularization term, the depth of the random forest, and learning rate and number of learners for Eta Boost. We did hyperparameter tuning for all classifiers and found that they greatly improved validation accuracy.
In the end, we found that random forest had the highest validation accuracy, though all classifiers performed fairly well with at least an accuracy of 77%.